Hello everyone, welcome to your favorite channel. This is Maths Zone African Motives, and we are still on our video series, Grade 10 Physical Science Mechanics section. So we have been doing an introduction part on mechanics where we started with the vectors and scalar quantities. Then we went on to motion in one dimension. Now we are now doing mechanical energy. So we have dedicated this time to dive deep into what is mechanics, because we saw that on our November final exam, mechanics consist of more than 40% of the whole question paper. So you'll be having on your physics part, you would be having a total of more than 70 marks, which is on mechanics only, from question number 1 up to the last question. So this is the reason why we are saying that let's dive deep and get a better understanding of what we refer to as mechanics. So now we are on our last part. So for those who actually joined us now, you are free to actually get to go back and watch our videos on vectors and scalar quantities, motion in one dimension, and then a video that is dedicated for past exam question papers, the practice that we brought for what we had done up until to motion in one dimension. So now we want to dive into mechanical energy. So this section is usually covered in term 4. According to the national ATP, you are supposed to be doing this section or not on term 4. But however, others would have done it already, or else maybe they are done with the syllabus. But now we want to dedicate our time in actually looking into what do we refer as mechanical energy, and the section itself, what does it foretells us? What is it are we expected to know? What is it that are we expected to be doing? So mechanical energy, you would find that it is responsible for most of the observable physical processes in our daily lives. For example, an object can just get to fall. Why? Because wheresoever it is falling from, it has got some energy, which we term energy due to height. And then the movement of cars, they are due to kinetic energy. Rolling of balls, roller coasters, etc. Most of these processes, they are due to what we refer to as mechanical energy. And what is mechanical energy? Mechanical energy can be defined as the sum of kinetic energy as well as potential energy. So you would actually get to say that your mechanical energy can simply be equal to kinetic energy plus gravitational potential energy. So mechanical energy simply relates to the motion and position of an object. But before we start diving deep into the principles and features of this, let's start by defining the word energy itself. What is it that we refer to as energy? We keep on saying mechanical energy, gravitational energy, potential energy, kinetic energy, electrical energy. What is energy? So you will see that energy, the word was derived from the Greek word energia, which refers or means activity or operation. So in universal convection, scientists later saw it easier to actually get to say that as long as someone is active, that person possesses what we refer to as energy. Whatsoever is making him active is what we refer to as what? As energy. Whatsoever is making maybe a machine or a machinery to be operational, it's what we refer to as energy. So energy can be defined as the ability to do work. As long as you are able to do work, you have energy. I'm sure you've seen some videos where they'll be advertising those energy drinks that you like to drink, where they'll be showing people maybe running, jumping, doing some extraordinary activities. They are simply trying to tell you that once you drink that energy drink, you now possess the ability to either jump, run fast, or do extraordinary work. You now have that ability. So that ability to perform work is what we refer to as what? As energy. And we know that all objects on earth, they possess energy. Why are we saying that? Because energy is closely linked to mass. As long as an object possesses mass, it certainly does have energy. And energy can neither be created nor destroyed. This is the law of conservation of energy, meaning to say that we only need to actually get to specifically define what type of energy that object will be possessing. It can either be kinetic, electrical, potential. For example, during winter, we just passed winter. During winter, people, you were actually bathing using warm water from your geysers. How come you were able to get warm water? It's because your geyser was able to transform electrical energy into heat. Same as people who have seen people in rural areas, if you actually get to burn wood or coal, you are able to cook. So you are transforming chemical into heat. So energy can neither be created nor destroyed, but it can only be transferred or converted from one form to another. So that is what we refer to as energy, the ability to do work, and all the object possessing that ability to do work due to their mass. And then in this chapter, we are going to be focusing on what we refer to as mechanical energy. And we have already alluded that mechanical energy is the sum of these two, gravitational potential energy and kinetic energy. So now let's start diving deep into what we refer to as mechanical energy. So there are types of mechanical energy, which we have said that it's gravitational potential energy and kinetic energy. So what we refer to gravitational potential energy as energy that is possessed due to height. So what is it that we mean by gravitational potential energy? Is that energy that you have as long as you are on top of some elevation relative to somewhat, to some selected reference point. So if we choose our ground here to be our reference point, it means that the height above this ground gives you what we refer to as what? As potential energy. Why are we saying that? Because we are saying that gravitational potential energy can be calculated using a formulation which says that potential energy, or else EP, is equal to the mass of the object times the gravitational acceleration on Earth times the height of elevation. So any object that is raised to a certain height above the reference level, it possesses what? Gravitational potential energy. So you would see that since we are saying that our ground is our reference point, it simply means that the height at our ground is equal to 0. So that anything above the ground would have a positive, what? A positive value, or else would have a meaningful height of elevation. So that's why we are choosing our ground to be the what? To be the reference point. So when you are defining gravitational potential energy, you have to state that it is that energy that an object will possess due to its position in the Earth's gravitational field relative to a selected reference. You can choose to actually get to use simpler words other than this by saying due to its height above a what? A selected reference point. By saying that, you would have defined what you refer to as what? Potential energy. Because we have to be above a certain reference point so that we can have a meaningful what? Height. Now, so you would see that M here stands for mass, and that mass has to be measured in kgs. Mass just referring to the total amount of substance within an object. And then G representing gravitational acceleration, which is to say when we are on Earth, gravitational acceleration is 9.8 meters per square second. But you know that if you go on moon, your gravitational acceleration would be 1.6 meters per square second. But according to our syllabus, we will only focus on the acceleration due to gravitational acceleration that is due to the what? To the Earth's gravitational field. So we'll be only on Earth. So this is the value that you are going to be using. And then H simply represent the height above a reference point. So you need to choose your reference point. So if you say your ground is your reference point, that means that when you are on this level, which is on the same level as the ground, it becomes to say your height is equal to 0. So that anything above the ground would be having a certain elevation height. And then after saying that, examples of objects that can possess gravitational potential energy is a book that is seated on a shelf. So by due to the height of that shelf, you would know that that book actually possesses what? Potential energy. Due to this height, which is above the ground. And then water stored in a dam. So you'd see that water that is stored in a dam, it is actually raised to a certain elevation. So that if the dam walls were to collapse, you will see that this water will start oozing to that side. Why will it start moving without being pushed? It's because of that potential energy that it possesses due to this height from the ground, as well as a ball which is on top of a roof. So allow me to just get to show you some examples which will refer to what? To object possessing potential energy. So you can see that here we've got a lady who is holding his ball, and that ball, at some point in time, she can either choose to release it. So when she releases this ball is capable of falling down this height up until to the ground. So what is it that is causing this ball to actually get to fall through or else to fall down this height unaided? It's what we refer to as what? As its potential energy, which we measure by a formulation which says what? Mass times gravitational acceleration times that height that it has. So these are the examples of what? Of gravitational potential energy. Anything that is raised, an object that is raised to a certain height, actually possesses what? That potential energy. For example, this ball that is on top of some stairs, you can actually get to give it an initial push. But once you've done that, it can start cascading down these steps because of the potential energy that it was having here. Now, after we have said that, let's try to go to the next type of mechanical energy. That is kinetic energy. Kinetic energy, from the word kinetic, this simply means motion. So anything that is in motion possesses kinetic energy. So kinetic energy is simply the energy possessed by an object as a result of its motion. So it can be calculated using this formula, which says that kinetic energy is equal to half mv squared. So we can either represent kinetic energy as Ke or else as Ek. So don't be confused if you find these two representations. They simply represent the same thing. So these are the normal notation or else usual notations that are used within your syllabus. They simply mean the same thing. So now this will be the mass of the object, and this will be the velocity of that object, the speed of the object relative or else in a certain direction. For example, a moving car, a ball, or else a soccer ball rolling. And then these are the examples of objects that can actually get to possess kinetic energy. You can see that we have got a flying aeroplane here. Because it is already flying, it is in motion. So anything that is in motion has got what? Kinetic energy. This woman is cycling because she's already in motion. Due to that cycling, she possesses what? Kinetic energy. A car moving. So from moving, you can see that there is what? There is motion. So that car also possesses what? Kinetic energy. And other examples include a windmill rotating, a boy on a skateboard skating, as well as a boy kicking a ball. These are the general examples of what? Of kinetic energy in action. Now, let's go to what we refer to as the law of conservation of mechanical energy. I'm sure you still remember when I introduced this topic, when we were defining energy, I introduced a law that we said is the law of conservation of energy, where we said energy can neither be destroyed nor created. We also have got a law of conservation of mechanical energy. And what do we mean by that? We are saying that in the absence of any dissipative forces, any wasteful forces, or else any opposing force of motion, we would actually get to know that the total mechanical energy remains constant. You would see that in the absence of non-dissipative forces such as air resistance or friction, the total mechanical energy remains constant. In some other instance, we will say that within a closed system, as long as we have got a what? A closed system, we would know that the total mechanical energy is what? Is conserved. That is what the law of conservation of mechanical energy says. It says that if we have a closed system, just know that an object within that closed system, its total mechanical energy will always be conserved or will remain constant. However, what are we saying? We are saying that that object can only be able to transform its energy from kinetic to potential forms, but the total amount of its energy will remain the same. For example, when maybe let's get to say that a ball is held on top of the building, like you saw from that lady, when it is held on top of that building, it is possessing its maximum gravitational potential energy. But once it's released, some of its potential energy is transformed into kinetic energy. That is what causes that object to start moving. And as it is moving down its maximum height to the ground, almost all of its gravitational potential energy would be transformed to the maximum kinetic energy. So you will see that when that ball reaches the ground, it will now be possessing maximum kinetic energy and zero potential energy. Or else we can use an example of a pendulum. I'm sure I can be able to explain this by using a pictogram. So let's use this pictogram to explain this law of conservation of mechanical energy. We are saying that if you are to take this pendulum ball and you swing it to its highest point that it can reach, at that highest point, it will be possessing what we refer to as what? Maximum potential energy. And then if this pendulum is within a closed system, let's say that this system is closed. If this system is closed, there are no any other forces. It's within a closed system. I'm sure you have seen these pendulums. If we release that pendulum ball, this ball will start cascading downwards, where its gravitational potential energy would now be transformed from potential energy to its kinetic energy. So what causes this ball to start moving is that transformation of our mechanical energy from one form to another. So at this point, this ball would be having a total mechanical energy. Let me say that a total mechanical energy that can be given by, so at point A, it will be having a total mechanical energy that can be given by its gravitational potential energy at A and its kinetic energy at A. But you will see that because it hasn't started moving yet, it is stationary. its velocity being equal to 0, this will also be 0. So you would be having what? Maximum gravitational potential energy at point A. When you release it, it will start moving. So some of the potential energy is now being converted to what? To kinetic energy. As the height, so you can see that the height is due to this elevation. So we'll take this reference level as our reference level. So let's say that this is our or else our reference level, because if I say ground, at some point in time this pendulum won't be able to reach the ground. So we will take this level as our reference point. So due to the height above this reference level, that is where we are going to be possessing what? Our maximum potential energy. But once it's released, you can see that the height starts decreasing. To say that if I'm at point, let's say 2 from point A, you would see that this height at point 2 is smaller than the height at point A. So where is this energy due to the what? To the reduction in energy gone? It has been transformed from what? From potential to kinetic. So you will see that when it reaches this reference level, which we have called our reference, which is 0 height, its gravitational potential energy becomes 0, but its kinetic energy becomes maximum. As its kinetic energy becomes maximum, this ball will not actually get to what? Stop there. It will continue moving up until it reaches a height which is of the same as its initial height where it started initially. Why? Because we said that our system is what? Is closed. As long as we are having a closed system, you swing this ball to its highest point, it will actually get to cascade down and later swing to a height that is equivalent to where it started. That is where it will having also its what? Its maximum potential energy. So we are saying that the conservation of mechanical energy simply tells us that the total mechanical energy within a closed system will always remain the same. But we can actually get to transform the type of energy from kinetic to potential. Now let's get to see how or else what we mean by whatever that we've been saying. So you would see that mechanical energy can be given by what? By the sum of kinetic plus potential. That is what? That is total mechanical energy. And then you would see that using the law of conservation of mechanical energy, as long as our system is closed and there are no what? There are no dissipative forces. So a closed system simply means that there are no dissipative forces. Our total mechanical energy at point 1, total mechanical energy at point 1 will be equal to total mechanical energy at point 2. Maybe I should use the conventional form that they are using here, where they are using EM. So my EM at point 1 should be equal to EM at point 2. So my EM, which is my mechanical energy at point 1, is given by what? It is given by EK, which is my kinetic energy, and my potential energy at point 1. So if I add these at point 1, they should give me the same when I add these at point 2. So you would see that this is at point 2. That is what we mean by conservation of mechanical energy. And we use this law to calculate missing values when we are told that the system is what? Is closed, when you are having a closed system. So here I've got an example of the law of conservation of mechanical energy. So we would get to say that we've got a ball here. This is our ball. And this ball has got a mass of 150 grams. And it is raised to a height of what? Of 3 meters. What is its potential energy? Its potential energy is going to be equal to mgh. So if I say 150 grams, I say that the mass has to be in kgs. So we need to divide 150 grams by 1000 grams in a kg, so that we get 0.15 kgs. So I'll be having 0.15 kgs times 9.8, which is the gravitational acceleration, times the height that I'm given here, which is 3 meters. You see that my potential energy at point 1 will be equal to what? It will be equal to 4.41 joules, or else 4.4 joules. And then, as I've said that, this ball is stationary initially, so its kinetic energy would be 0. But due to the law of conservation of mechanical energy, when we release this ball, when it reaches a height of 0.5 meters, its total mechanical energy has to remain as its initial. So initially, what was our total mechanical energy? Initially, our total mechanical energy would be given by our total what? EM at point 1 would be equal to what? Let's get to say potential energy at point 1 plus kinetic energy at point 1, which is just what? 4.4 joules plus 0 joules for kinetic energy, which gives you what? 4.4 joules. So like I said, initially you'll be having a maximum potential what? Energy. That makes up your total what? Total mechanical energy. So you'll be having a total, you'll be having a maximum potential energy, and this maximum potential energy makes up the total mechanical energy because the kinetic energy will be 0. But when it falls to this height, we are saying that the total mechanical energy at point 2 still has to remain as 4.4 joules. So this is what we mean by here when we say that our mechanical energy has to be conserved. So if we are to sum kinetic energy at point 1 and kinetic energy at point 2, it has to give us the same value if we sum kinetic energy at point 2 and potential energy at point 2. And that value has to remain constant as what? As 4.4, the one that we have calculated initially here. So if you now want to find the kinetic energy of this ball, because definitely this ball, since it is rolling from this position, cascading downwards, when it reaches here, it will be having a certain velocity. If you want to know that velocity now, this is where you say kinetic energy at point 2 plus potential energy at point 2 has to be equal to 4.4. Now, since we know the height, let's try to calculate the velocity of that ball at that point. We now want to calculate the velocity that is at point 2. You would come here and say half mass v2 squared plus mgh2 should be equal to 4.4. Now, our mass is 0.15 times 9.8 times the height here, it's now 0.5 equal to 4.4. And then for this one now, our mass, we know that it's 0.15, but we do not know the velocity squared, and this one is half. So we can transpose this that other side. So if you say 0.15 times 9.8, and then you later multiply by 0.5, you would see that it becomes 0.735. So here you'd be having 0.735 joules, and this side you'll be having 4.4 joules. And this side you would be having what? Let's get to say half of 0.15 times v2 squared. So to get this, you transpose this side and then you later divide throughout by that, and then you square it. So your v2 here definitely will be equal to 4.4 minus 0.735, and then divided by this bracket 0.15 all over 2, and then you square root. You would see that if you do that, you are supposed to get a value of what? 4.4 minus 0.735, and then you later divide the final answer by you get 48.866. So if you find this, the square root of 48.866, you would find that this side you would be having a velocity of what? Of 6 meters per what? So it would be 6.99. So it would be approximately 7 meters per second. you would be having a velocity of 7 meters per second. This is approximately. So we have used our total mechanical energy theorem to find what? To find our velocity. So that is how we apply this what? This law of conservation of mechanical energy. Now let's look into another example. Now we are told that we have got a woman and this woman is on a phone. They're saying that a woman is at the shopping mall 10 meters above the what? The ground. Her cell phone with a mass of 0.01 kg falls and hits the ground at a speed of 40 meters per second. They are now saying ignore the effects of air resistance. Once they say this, they are simply telling you that assume that your system is closed. You have got a closed what? A closed system. Once we have a closed system, what do we have? We know that the total mechanical energy will be what? Will be conserved. So in questions to come, take note of this. Once they tell you that ignore air resistance, just know that they are telling you that the system is closed for this scenario. So your total mechanical energy is what? Is conserved. That is what it simply means there. Now, they are saying convert first 14 meters per second to kilometers per hour. So if you still remember what we did when we were doing motion in one dimension, we mentioned that we have got a conversion factor from what? From meters per second to kilometers per hour, or else from kilometers per hour to meters per second. And that conversion factor, we say that it is 3.6 kilometers per hour. So if you are changing from meters to kilometers per hour, you multiply this 14 meters per second by 3.6 kilometers per hour, because we are saying that 1 meter per second is equivalent to 3.6 kilometers per hour. So if I multiply, I would be able to get a value of what? So if I come here and then I say 14 meters per second times 3.6 kilometers per hour, I would get a value of 50.4 kilometers per hour. If you are converting from kilometers per hour to meters per second, you divide by that 3.6. So that if you say 50.4 kilometers per hour divided by 3.6 kilometers per hour, this will give you 14 meters per second. So if you are moving from kilometers per hour to meters per second, you divide. If you are moving from meters per second to kilometers per hour, you multiply by 3.6 kilometers per hour. So that is what you were just supposed to do there. Now let's go to our following questions. So I know that we are going to use this diagram, so we'll keep on coming back to this diagram. The question is now saying, define what we term kinetic energy. We say that kinetic energy is the energy of an object that is possessed due to what? To motion. Of an object due to its motion. As long as there is movement, that object possesses what? Kinetic energy. So it is the energy of an object due to its motion. Now calculate the gravitational potential energy of the cell phone at a height of 5 meters above the ground. We know that gravitational potential energy is calculated by mgh. So I need the mass of the cell phone, I know the gravitational acceleration, and I've been given the height. What was the mass that was given there of my cell phone? They say that the cell phone has got a mass of 0.01 kgs. So that is what I'm going to use there. So I'll just go and use 0.01 kgs times 9.8, then times 5 meters, which is my height. And if I do that, what is the value that I'm going to get for my gravitational potential energy? If you use your calculators, you are supposed to find, because my calculator is giving me 0.49 joules, 0.49 joules. So energy is measured in joules. Just know that energy is measured in what? In joules. Either is it kinetic, gravitational potential, or mechanical. They are all measured in joules, which is represented by the letter G. So here for 5.4, our answer was just going to be 0.49 joules. And energy, it's a scalar quantity. It has no direction. You only mention its what? Its magnitude. And then now they're saying, calculate the velocity of the cell phone at a height of 5 meters above the ground. Now we need to go back to the diagram and get to see what's happening at 5 meters above the ground. So 5 meters above the ground, it's halfway through as it is falling. So initially the cell phone was having an initial velocity of what? Of 0. So its kinetic energy definitely was equal to what? To 0. But its potential energy was due to the height of 10 meters. So it was going to be equal to 0.01 times 9.8 times 10. That becomes the maximum gravitational potential energy there. So now they are saying when you are now 5 meters above the ground, what is the velocity there? So I want to show you something. We say that if our mechanical energy is conserved, let's say that our mechanical energy is conserved, I want to use this opportunity to show you something. I would move this aside. If, let's say, for example, I have got an object that is above the ground at a certain height, and this is my ground, and I term my ground my what? My reference point. Simply means that the height above the ground here, at some point in time, it's equal to what? To h. And then my potential energy here at 1 will be given by mgh, which is my maximum height. And my kinetic energy here, it will be given by what? Half mv squared, which is at 0.1. So at 0.1 here, if I've got an object which is stationary, and then it falls to the ground to 0.2, and they tell me that I have to ignore air resistance, ignoring air resistance. What it means is the system is closed. We are having a closed what? We are having a closed system. Once my system is closed, it simply means that my total mechanical energy at 0.1 should be equal to my total mechanical energy at what? At 0.2. So what is my total mechanical energy at 0.1? So you would know that by law of conservation of energy, we are saying that total mechanical energy at 0.1 should be equal to total mechanical energy at what? At 0.2. Now, what is total mechanical energy at 0.1? That will be equal to potential energy at 0.1 plus kinetic energy at 0.1. And then what about total mechanical energy at 0.2? It is potential energy at 0.2 plus kinetic energy at 0.2. When this ball reaches the ground, that instant before it hits the ground, we are on the same level with the ground. The potential energy would be equal to 0. When it was at height h, its kinetic energy was equal to 0. So you can simply see that if I now get to come and actually get to put what I've said here in this equation, at some point in time, you would see that this equation would get to say that my potential energy at 0.1 should be equal to my kinetic energy at point what? At 0.2, given that we are on this ground. We are saying that the total mechanical energy has been converted to the what? The total potential energy has been converted to the total kinetic energy. And this is where we can actually get to use the scenario to say that for us to calculate maybe the height or velocity, if I know the height here, I would say mgh should be equal to what? To half mv max squared. So that if I want to know the velocity here, I'll multiply throughout by 2. It will be 2 mgh. And then I would have mv max squared here. But the mass is the same. If I divide throughout, these ones will cancel out. So I'll be left with 2hg being equal to v max squared. So if I now get to root this side and I root that side, you would see that my velocity, my maximum velocity will simply be given by what? My v max will simply be given by root of 2 times gravitational acceleration times my maximum height. So I can actually get to use this equation to find my maximum velocity, given that my system is closed and I'm now at the ground, starting from the maximum height. But here, the scenario is a bit different. I just wanted you to have a picture of this. But here, the scenario is a bit different. In what way? In what way? We are not reaching the ground. We are still at a certain elevation. So since we are still at a certain elevation, we still need to use the conservation of mechanical energy principle. So I'm saying that we are still at a certain what? Elevation. So allow me to just get to wrap this information so that we can go back to our question. So here we are still at a certain what? At a certain elevation. What do we mean by that? They said, what is the velocity of the cell phone when it is now 5 meters above the ground? So we are 5 meters above the ground. But you can see that we started at 10 meters above the ground. So the difference here between 10 meters and 5 meters, it gives you a picture of the potential energy that was converted to what? To kinetic energy. And that kinetic energy is the one that is going to give you the what? The velocity there. So what we do here, we just come and use our conservation of mechanical energy, and then we get to say that our total mechanical energy at point 1 has to be equal to the total mechanical energy. Let's get to say that we are at point 2 and this is point 3. So I would say this is point 1, this is point 2, and this is point 3. But we only want to look at point 1 and point 2. So these two, they have to be equal. But this one is given by potential energy at point 1 plus kinetic energy at point 1, which is equal to my mass there, it's 0.01 times my gravitational acceleration, 9.8 times 10, plus the kinetic energy here, it's 0 because it was stationary before it fell. So this one is 0. So the total mechanical energy at point 1 there will simply be equal to what? It will be 0.01 times 9.8 times 10. And that gives you what? It gives you 0.98 joules. It becomes 0.98 what? Joules. That is the total mechanical energy that we have at point 1. This same value, we have to find it on point 2, which is also given by potential energy at point 2 plus kinetic energy at point 2. And the potential energy at point 2, its mass, which is 0.01 times, or else let me just use mgh so that you can see. So at point 2, we have got mg, and then the h is now 5 meters, plus the kinetic energy is half mass times the velocity there squared. So we are looking for this velocity. Since we have everything here, and then on this other side, we say this is equal to that. So this value becomes 0.98 joules. Since we have got the value this side and the value of everything here and the value of the mass, we can find the velocity by just substituting what we know. So already we know that this is what? 0.98 and this is 0.01 times what? It is times 9.8 times 5. And then this one is a half of what? 0.15. And then this one is v squared. Sorry, this one is 0.01. Now I'm now using the information for the last question. Sorry, guys. This is 0.01. So we are looking for this velocity. So the first thing is to transpose this to that other side. So we already calculated this initially and we found 0.49 joules. So we just get to say 0.98 minus 0.49. And then it will give you what? 0.01 all over 2 times v squared. And we are looking for this v squared. So maybe I can actually get to take this to a bigger space so that we can actually get to 4. So we are saying that we're just supposed to come. Let me just get to erase so that I decongest this so that you can see clearly. So we say that mechanical energy at point 1 has to be equal to mechanical energy at point 2, which is equal to mechanical energy at point 3. So that is what we want to show. This is given by potential energy at point 1 plus kinetic energy at point 1, where this is also given by potential energy at point 2 plus kinetic energy at point 2, which is also equal to potential energy at point 3 plus kinetic energy at point 3. Now let's feed in information that we have. We have this information at point 1. That is what we said. It's equal to what? 0.98 joules. But this one is 0. And then the information here we said it's 0.49. And then this one is what we are looking for. That is half of 0.01. That becomes half of 0.01. And then the velocity squared. So we are looking for this value. So since we are looking for this value, we say that we're going to transpose this side. That side, it will be 0.98 joules, 0.98 minus 0.49 joules. So these ones, they will subtract, and then we'll be left with 0.01 all over 2, and then we multiply by what? V2 squared, because we are looking for velocity at 5 meters, which is V2. I multiply throughout by 2 and divide by 0.01, the difference here. The difference this side just becomes 0.49. And then I would multiply it by 2, this 2. And then I would divide it by this 0.01. So that this side I can only be left with V2 squared. And then I will root this side, and then I will root this side. And then after rooting, I would be able to find my velocity 2. So if I actually get to say that root of that, let me use my calculator. The value that I'm going to find there is supposed to be equal to 9.899. So it becomes what? Simply becomes 9.9 meters per second. That becomes my V2. So let's punch our calculator and cross-check that. I just said the root of 0.49 times 2 divided by 0.01. That gives you that velocity. So that was the velocity that you are supposed to look for there. So the velocity here at 5 meters, we say that our velocity would be equal to what? 9.9 meters per second. So you can come and say 9.9 meters per second, 9.9 meters per second. And we used the principle of conservation of what? Of mechanical energy. Now they're saying, will the value of the cell phone's mechanical energy just before it hits the ground be greater than, less than, or equal to mechanical energy at the height of 5 meters? Explain your answer. It is going to be the same, which is equal to. Why? Because we are saying that the system is closed. We have got a closed what? We have got a closed system. That is how we do it. There is no need of explaining there. You are just supposed to come and say it is going to be equal to. They are asking you if the mechanical energy at this height, let me show you. If the mechanical energy at this height, 5 meters, would be equivalent to that height, which is at the just before it reaches the ground. So just before it reaches the ground is 0.3, and here we said it's 0.2, and here it's 0.1. We say that the total mechanical energy in each and every point has to remain constant, because we are saying that this is a what? This is a closed system. Why? Because there is no air resistance. So here you answer that you were supposed to just get to write. Here you were supposed to say equal to, because they said will the value of the cell phone's mechanical energy before it hits the ground be greater than, less than, or equal to mechanical energy at height 5 meters? It would be equal to. Why? Because there are no dissipative forces, or else the system is closed, because the system is what? Is closed. So you choose which reasoning do you want to use there. The system is closed, or else there are no dissipative forces, so it will be equal to. So guys, that was our introduction to mechanical energy, and that is to do with mechanics. So now let's meet on the next videos to come, when we are now revising the full papers of November past question papers, when we are now actually preparing for our finals. So you will see that also the mechanics, which includes vectors and scalar quantities, as well as motion in one dimension, and the mechanical energy part will be there as well. So thank you guys for being together. Let's meet in our next coming videos.